Our universe is not just expanding, it is accelerating into an unknown future. This relentless push defines the cosmic dark energy era, the single longest chapter in the story of everything from now until the end of time. And yet, for something that makes up nearly 70% of the cosmos, we have almost no idea what it actually is. By the end of this journey, you will understand the 25 greatest puzzles that dark energy presents, from the fate of reality itself to the strange coincidences that suggest our place in the cosmos might be profoundly unusual. We will explore why the vacuum of space should be tearing itself apart, why we seem to live at a uniquely special moment, and whether the universe's ultimate destiny is a frozen silence or a violent rip. What single cosmic mystery keeps you up at night wondering? That acceleration is powered by the universe's greatest unknown. The first and most fundamental mystery is the nature of dark energy itself. We have a name for it, and we can measure its overwhelming effect, but we have no idea what it is. Think of it this way. For most of cosmic history, gravity has been the great architect pulling matter together to form galaxies, stars, and planets. Dark energy is the opposite force. It is a kind of cosmic repulsion, a pressure inherent to empty space that pushes the universe apart. While dark matter, another mystery, acts like an invisible glue holding galaxies together through gravity, dark energy works on the vast emptiness between galaxies, stretching the very fabric of the cosmos faster and faster. So what could it be? The leading idea, one that goes back to Albert Einstein himself, is called the cosmological constant. This proposes that dark energy is not a thing at all, but a fundamental property of space. Even in a perfect vacuum, empty space has a tiny, intrinsic energy. As the universe expands and more space comes into existence, this vacuum energy adds up, generating the repulsive force we see. The problem is, when physicists try to calculate how strong this vacuum energy should be using our best theories of quantum mechanics, the number they get is catastrophically wrong. It predicts an expansion so violently fast that stars, planets, and even atoms could never have formed. The theoretical value is off by a factor of 1 followed by 120 zeros. It is the worst prediction in the history of science. The other major candidate is called quintessence. This imagines dark energy as a dynamic energy field that fills space, similar to the field thought to have powered the Big Bang's inflation but far weaker. Unlike a constant property of space, quintessence could change over time, its strength ebbing and flowing. This would mean the acceleration of the universe might not be forever. It could slow down or even reverse one day, but quintessence brings its own puzzles. We have no evidence for this new field, no particle associated with it, and its proposed behavior feels to some scientists like an ad hoc explanation to make the math work. Then there is the most radical possibility. What if dark energy is not a new substance or a property of space, but a sign that our understanding of gravity itself is incomplete? Einstein's theory of general relativity has passed every test thrown at it for over a century, but it has never been tested on the scale of the entire observable universe. Perhaps on these largest of scales, gravity behaves differently, and what we call dark energy is just gravity weakening in a way we do not yet understand. This would mean rewriting the most successful theory in physics, so the core mystery remains stark. Is dark energy a static feature of the cosmos, a changing field, or a colossal clue that we have misunderstood the universe's most fundamental force? The answer defines everything that comes next. This staggering mismatch is not just a minor error. It is the cosmological constant problem, and it represents the single largest gap between prediction and reality in all of science. Quantum field theory, our most successful framework for describing the subatomic world, tells us that the vacuum of space should be a seething, bubbling foam of virtual particles popping in and out of existence. This quantum jitter gives every cubic centimeter of so-called empty space an enormous intrinsic energy. When you add up all that energy across the observable universe, the repulsive force it creates should be so powerful that the cosmos would have blown itself apart in a fraction of a second after the Big Bang. Reality, however, tells a completely different story. The actual dark energy we measure is mind-bogglingly weaker. To put the scale of this error into perspective, if the theoretical prediction for vacuum energy were the size of the entire observable universe, the amount we actually observe would be smaller than a single atom. It is like calculating that a gentle breeze should have the force of 1 trillion hydrogen bombs. The number is off by a factor of 1 followed by 120 zeros. This is not a problem you can fix with a slight adjustment. It suggests something profound is missing from our picture of physics. This leads directly to the fine-tuning problem. Why is the cosmological constant so incredibly, inexplicably small, yet not exactly zero? If it was zero, the universe would expand at a slowing rate forever, a cold but stable fate. If it were even slightly larger, as the quantum theory suggests it should be, galaxies would never have formed. For life, for stars, for planets to exist, the value had to be balanced on a razor's edge. This feels unnatural. In physics, a number that requires such precise, unlikely adjustment to allow for our existence is seen as a clue. It begs the question, is our universe somehow specially engineered, or is there a deeper explanation? One unsettling possibility is the multiverse. If our cosmos is just one bubble in an infinite froth of universes, each with different physical constants, then it is no surprise we find ourselves in one of the rare, finely tuned bubbles where the numbers allow for galaxies and life. We are here because we could not be anywhere else. The alternative is that there exists some unknown, elegant symmetry or cancellation mechanism in physics that naturally drives the net vacuum energy to nearly zero. We simply have not discovered it yet, so the cosmological constant is more than a number. It is either a signpost pointing to a vast landscape of unseen realities, or it is the glaring error that will finally force us to rewrite the laws of quantum physics and gravity into a unified whole. The vacuum of space is not empty, and its quiet hum holds the key to either our profound loneliness or our unimaginable company. This fine-tuning leads to an even stranger puzzle, one that feels less like a calculation error and more like a cosmic prank. Right now, at this very moment in cosmic history, the energy density of dark matter and the energy density of dark energy are almost exactly the same. They are within a single order of magnitude of each other. Think about that for a second. For billions of years, the universe was dominated by matter. Its gravitational pull controlled the expansion, slowing it down. Dark energy, if it was even present, was an utterly insignificant whisper in the background. Then, roughly 5 billion years ago, something shifted. As the universe expanded and matter diluted, dark energy's constant presence began to assert itself. We have now entered the dark energy era, where this mysterious repulsion dictates our future. But here is the bizarre part. We just so happen to be living in the brief sliver of cosmic time when these two titanic forces are in a near-perfect balance. This is the coincidence problem. Why now? The universe is 13.8 billion years old. The matter-dominated era lasted for over 8 billion years. The dark energy era that we have just entered will last for trillions upon trillions of years, essentially forever. The transitional period where their densities are comparable is a blink of an eye on the cosmic calendar. And yet, here we are, conscious observers, alive to see it. It is as if you walked into a movie theater and the film started precisely at the moment the hero first appears on screen. The odds seem astronomically against it being random chance. So what is going on? One unsettling answer is the anthropic principle. This is the idea that our observations of the universe are not random, but are constrained by the fact that we exist to make them. In a universe where dark energy dominated too early, matter would never have clumped into galaxies and stars. In a universe where matter remained dominant forever, the expansion might eventually collapse back in a big crunch, cutting any story short. Perhaps only in universes where this brief balancing act occurs can complex structures, planets, and life arise. We do not see a special time. We see the only time that could produce beings capable of seeing anything at all. It is a cosmic version of the survivor's bias, but for many scientists, this feels like giving up. It swaps a scientific explanation for a philosophical one. The alternative is that this is not a coincidence at all. Perhaps dark energy and dark matter are not separate, unrelated entities. Could there be a hidden link between them? Some theories propose a unified dark fluid, a single substance whose properties change as the universe evolves, acting like matter in the past and like dark energy in the present. Others suggest interactions between the two, where one slowly decays into the other, orchestrating this precise handover of power. If true, our epoch is not lucky. It is inevitable, a direct consequence of a deeper law we have yet to uncover. So the coincidence problem forces a profound choice. Are we living in a staggeringly rare universe, one of countless others where the numbers just happen to line up for us? Or is the apparent balance a glaring clue, a signal that dark energy and dark matter are two sides of the same enigmatic coin, waiting for a bold new theory to reveal their connection? The answer tells us whether we are cosmic lottery winners or simply readers of a universe that has been leaving us hints all along. The choice between a static force and a changing one is not just academic. It is the single most important question for predicting the ultimate fate of everything. So, is dark energy truly constant? To answer this, astronomers have become cosmic detectives, searching for the slightest change in its push across the vastness of time. They are looking for a deviation from the simplest model, Albert Einstein's cosmological constant, which says dark energy's strength is fixed and eternal. The alternative is quintessence, a dynamic field that could be strengthening, weakening, or even switching its behavior entirely. Finding out which is true requires measuring the expansion history of the universe with exquisite precision, looking billions of years into the past. The primary tool for this is still the same cosmic mile marker that first revealed acceleration, Type 1, a supernova. By comparing how bright these standard candles appear with how much their light has stretched or redshifted, scientists can chart how fast the universe was expanding at different epochs. If dark energy is constant, the data will follow one very specific curve. If it is changing, the curve will bend differently. But supernovae are not the only clue. A second method uses the frozen echoes of the early universe, patterns called Baryon acoustic oscillations. In the first 400,000 years after the Big Bang, the cosmos was a hot, dense soup of particles and light. Pressure waves, like sound waves, rippled through this plasma. When the universe cooled enough for atoms to form, freeing the light that we now see as the cosmic microwave background, those waves froze in place, leaving a faint, statistical imprint of spheres within the distribution of galaxies. By measuring the size of these spheres at different distances and thus different times, astronomers have a standard ruler stretching across cosmic history. Any change in the expansion rate will subtly alter how that ruler appears to us. Finally, the cosmic microwave background itself provides a snapshot of the universe when it was only 0.003% of its current age. By combining this baby picture with measurements of how structures clump together in the more recent universe, scientists can infer how much dark energy was present and how it has behaved. The goal of projects like the Dark Energy Survey and the upcoming Vera-C Rubin Observatory is to apply all these methods on an unprecedented scale, mapping billions of galaxies and discovering millions of supernovae. What would it mean if they found dark energy is not constant, everything changes? If quintessence is weakening, the acceleration of the universe could someday slow, perhaps even allowing gravity to regain control in a distant future. If it is strengthening, the cosmic acceleration could become runaway, leading to a far more dramatic and destructive end. The simple, frozen future of the cosmological constant is replaced by a universe of possibilities, some serene, some terrifying. The quest to measure this invisible pressure is a race to read the final chapter of our cosmic story before the ink has even dried. The possibility of a dynamic dark energy opens the door to a fate far more violent than a slow, cold expansion. This is the Big Rip, the most dramatic and destructive end our universe could face. Picture the fabric of space itself not just stretching, but stretching with ever-increasing ferocity. If dark energy is a form of quintessence that grows stronger over time, its repulsive force would eventually overcome every force that holds reality together. It would start on the largest scales. First, the gravitational glue binding clusters of galaxies together would be severed. Galaxies would fly apart into the growing void. Then the force would reach inside our own Milky Way, pulling stars away from each other. As the acceleration turns catastrophic, it would target our solar system. The Sun's gravity would be too weak to hold its planets. Earth would be flung into the endless dark, but the horror would not stop there. The rip would come for our planet itself, overcoming the gravity that shapes it into a sphere. Mountains, continents, and oceans would be torn from the bedrock. Finally, in the last moments, the force would reach down to the molecular and atomic levels. The bonds between atoms would snap. Nuclei would be shredded from their electrons. Every piece of matter in the universe would be reduced to a spray of disconnected, fundamental particles, alone in a space-time tearing itself apart at infinite speed. All of this could happen in a finite future, perhaps hundreds of billions of years from now, but on a cosmic calendar, it is a sudden and definitive end. This stands in stark contrast to the more gentle, but no less final, fate of the cosmological constant model, the heat death or big freeze. In that scenario, dark energy is constant. The universe expands forever, but at a rate that never becomes strong enough to tear bound structures apart. Galaxies will remain gravitationally bound islands, but stars will slowly burn out over trillions of years. New star formation will cease as gas clouds are spread too thin. Black holes will eventually evaporate via Hawking radiation. The universe will approach a state of maximum entropy, where no energy gradients exist to do work, no light shines, and no complex processes are possible. It is a quiet, frozen silence stretching into eternity. The difference between a rip and a freeze hinges on a single, critical number that cosmologists call the equation of state parameter, denoted by the letter W. This parameter describes the relationship between the pressure and density of dark energy. For a simple cosmological constant, W equals exactly -1. If W is exactly -1, we get the heat death. But if W is less than -1, meaning the pressure is more negative, more repulsive, then dark energy strengthens with time and the big rip becomes inevitable. Our current best measurements from supernova, the cosmic microwave background, and galaxy clustering all point to a value incredibly close to -1. The data is consistent with a constant dark energy, but the uncertainty in the measurement still leaves a tiny, terrifying window open. We cannot yet rule out that W is, for example, -1.001. That minuscule deviation over tens of billions of years would be enough to seal the universe's violent fate. So every new galaxy survey, every new supernova observation is not just collecting data. It is a measurement of the ultimate tensile strength of reality itself, searching for the first hint of a tear in the cosmic fabric that will determine how the final story ends. The ultimate fate of the cosmos hinges on a single number, but what if we cannot agree on what that number is? This is the Hubble tension, a growing crisis that threatens to crack the very foundation of modern cosmology. It centers on the Hubble constant, the rate at which the universe is expanding today. For decades, cosmologists have worked to pin down its precise value, but instead of converging on an answer, our two best methods are stubbornly drifting apart, creating a rift that may point to something profoundly wrong with our understanding of the cosmos. One method looks back to the universe's infancy. By studying the detailed patterns in the cosmic microwave background, the afterglow of the Big Bang, scientists can use the standard model of cosmology to run the cosmic film forward. They input the physics of the early universe, account for dark matter and a constant dark energy, and the model spits out a prediction for what the expansion rate should be today. This early universe measurement is incredibly precise. It gives us a Hubble constant of about 67 kilometers per second per megaparsec. This means for every megaparsec, a distance of about 3.3 million light-years, a galaxy appears to be moving away from us 67 kilometers per second faster. The other method measures the universe directly in its present mature state. Astronomers use a cosmic distance ladder. They start with nearby stars called Cepheid variables, whose predictable pulsations allow us to know their true brightness. By comparing that known brightness to how dim they appear, we can calculate precise distances to nearby galaxies. Then, in those galaxies, they find Type 1, a supernova, the same standard candles that reveal dark energy. By linking the Cepheid distances to the supernova brightness, they can calibrate the entire ladder and measure how fast those supernovae are receding from us. This late universe method, championed by teams using the Hubble Space Telescope, gives a significantly faster expansion rate, around 73 kilometers per second per megaparsec. The difference seems small, only about a 9% discrepancy, but in the world of high-precision cosmology, it is a glaring 5 sigma chasm. The error bars on each measurement have shrunk so much due to better data that they no longer overlap. This is not a case of sloppy measurements. It is a direct conflict. It is as if you used a blueprint to predict the exact height of a fully grown tree. But when you went out and measured the actual tree with a tape measure, it was noticeably taller. One of our tools is lying to us, or our blueprint is wrong. The immediate suspicion falls on systematic errors. Perhaps there is something we do not understand about Cepheid stars, or hidden dust is affecting the supernova measurements. Yet, as teams scrutinize their data and new instruments like the James Webb Space Telescope join the hunt to cross-check the distance ladder, the tension persists. It refuses to go away. This leads to the thrilling, unsettling possibility that the discrepancy is real, and it is a clue. The standard model, known as lambda CDM, with its constant dark energy and cold dark matter, might be incomplete. Perhaps dark energy is not constant after all, but evolved in a way we did not anticipate, causing the expansion rate to shift between the early and late universe. Maybe there is an additional, unknown type of neutrino or some other exotic particle that subtly changed the universe's early energy balance. Or, most radically, it could indicate that the fabric of space-time itself has properties that change over cosmic time, a flaw in Einstein's gravity on the largest scales. The Hubble tension is more than a technical disagreement. It is a direct challenge to our standard model of the universe. If it holds, it means our cosmic storybook has a fundamental inconsistency between its first chapter and its last. Resolving it will either force us to find a hidden error in our most cherished observations, or to rewrite the laws that govern the cosmos from its first moment to its last. The fate of the universe may depend on a number we cannot yet agree upon. Our inability to agree on the universe's expansion rate points to a deeper, more unsettling possibility. What if the acceleration we measure is not a global truth about the cosmos, but a local illusion? This brings us to the seventh mystery, the idea that we might be living inside a cosmic anomaly of unimaginable scale, a place where the rules appear different simply because of where we are standing. This is the KBC void, named for the scientists who proposed it, and it challenges the very foundation of the dark energy discovery. The core principle of modern cosmology is the Copernican principle, the idea that our place in the universe is not special or central. We assume that on the largest scales, the cosmos is homogeneous and isotropic, meaning it looks roughly the same in every direction and from every location. This assumption is what allows us to take observations from our single vantage point and apply them to the entire universe. But what if, on a scale we have only recently been able to survey, that assumption is wrong? The KBC void hypothesis suggests exactly that. It proposes that our Milky Way galaxy resides inside a vast, bubble-like region of space that is significantly emptier than the cosmic average. This void would span an astonishing 1 billion light-years across or more, a staggering expanse of below-average density. In such a place, the local gravitational landscape is different. With less matter around us to pull things together, the space inside the void would expand faster relative to the denser, matter-rich regions outside. From our perspective, sitting in the middle of this underdensity, galaxies would appear to be fleeing from us at an accelerated rate, not because of a mysterious dark energy pushing them, but because we are in a gravitational valley and everything is sliding down the hills toward the denser walls. It is a cosmic illusion of our own making. The evidence for such a void comes from large-scale galaxy surveys. When astronomers map the distribution of galaxies and galaxy clusters, they do find that our local neighborhood, out to hundreds of millions of light-years, is less crowded than standard models predict. We seem to be in a relative clearing, with immense superclusters like the Shapley concentration lying just beyond its proposed edge. Proponents of the void model argue that when you properly account for this underdensity, the observed acceleration can be explained by the laws of general relativity alone, without the need for any dark energy at all. It would mean that Einstein's theory with just ordinary matter and gravity is correct, and we have simply misread the cosmic map. The cosmology community is fiercely divided on this idea. Critics point to the extreme fine-tuning such a void would require. To mimic the observed acceleration, it would need to be nearly perfectly spherical, and we would need to be located almost exactly at its center. This would violate the Copernican principle in the most dramatic way possible, making our location not just unusual but uniquely special. Furthermore, the cosmic microwave background, the uniform glow from the early universe, places tight constraints on how large and how underdense any local void can be. The observed smoothness of that background radiation suggests that if we are in a void, it cannot be too deep or too sharp-edged. The debate rages in academic journals and conferences. Is the KBC void a real structure that forces us to reconsider our place in the cosmos, or is it a statistical fluke, an overinterpretation of data that will vanish with better surveys? The upcoming era of telescopes like the Vera C. Rubin Observatory will map the universe in unprecedented detail, either confirming this billion light-year emptiness or finally ruling it out. If the void is real, it would be one of the most humbling discoveries in history, revealing that our entire understanding of cosmic destiny was skewed by a trick of perspective. We would have to accept that we live in a quiet backwater, and the grand acceleration of the universe might just be the view from our particular window. The possibility of a cosmic void forces us to question our most basic assumptions about the universe's uniformity. But even if our location is perfectly ordinary, the relationship between its two dominant shadows remains deeply puzzling. This brings us to the eighth mystery. Could dark energy and dark matter be interacting? Right now, our standard model treats them as entirely separate entities. Dark matter clumps together through gravity, providing the scaffolding for galaxies. Dark energy is a smooth, repulsive force that fills empty space, pushing the scaffolding apart. They are like two actors on a stage who never speak to each other. One building sets while the other slowly expands the theater. But many cosmologists suspect this is a flawed script. The eerie coincidence that their energy densities are comparable today hints at a hidden connection. What if these two dark giants are not strangers but are in a constant, subtle dialogue? Theoretical models exploring this idea propose a direct, non-gravitational interaction. Imagine dark matter particles as they move through the cosmos, somehow exchanging energy with the dark energy field. This interaction could be a slow decay where dark matter particles gradually convert into dark energy. Over billions of years, this process would naturally orchestrate the transition we observe. As matter dilutes with expansion, this decay would ensure dark energy's influence grows to match it, solving the coincidence problem not by luck but by physics. The universe's handover of power would be a direct consequence of a fundamental link. Alternatively, the interaction could work in reverse, with dark energy fueling the creation of new dark matter. Or it could be a continuous energy transfer that alters how both components evolve. The consequences would be profound for the growth of cosmic structure. Dark matter's gravitational pull is what allows ordinary matter to condense into galaxies and clusters. If dark matter is slowly decaying into dark energy, its clumping power would weaken over time. This would leave a distinct fingerprint on the universe's large-scale architecture. Galaxy clusters would be less massive than we predict. The cosmic web of filaments and voids would appear more diffused. So how do we search for this invisible conversation? Astronomers turn to the most massive collapsed structures in the universe, galaxy clusters. By measuring the number and distribution of these clusters across cosmic time, we can trace the growth of structure. If dark matter is interacting and losing its clumping strength, we should find fewer giant clusters in the recent universe than our standard, non-interacting models forecast. Another method involves studying the subtle distortions of light from distant galaxies, a technique called weak gravitational lensing. The way dark matter bends light reveals its distribution. An interacting dark sector would create a specific pattern in this lensing map, a signature of matter clumping that slowed down prematurely. Current data from surveys is beginning to place constraints on these models, but the evidence is not yet conclusive. We are listening for a whisper in a cosmic storm. Discovering an interaction would be a revolution. It would unify the universe's two greatest mysteries into a single, elegant framework. Dark energy and dark matter would become two aspects of one enigmatic substance, a unified dark sector whose dynamics wrote the entire history of the cosmos, from the first galaxies to the accelerating future. The search for this link is a hunt for the hidden grammar of the universe, the rule that connects its silent builder with its relentless expander. While dark energy dominates our present, its shadow may have been cast in the universe's first moments. The ninth mystery is the startling idea of early dark energy, a transient, supercharged version of the force that could have briefly flared into existence when the cosmos was less than a second old. This is not the same dark energy we see today, but a hypothetical, short-lived field that would have dramatically altered the universe's infancy before vanishing without a trace. Its proposed purpose is profound: to solve the Hubble tension. Recall the conflict between the early universe's prediction for the expansion rate and the faster rate we measure locally. Early dark energy offers a potential fix. In the standard model, the universe transitions from a period of rapid inflation to an era dominated by radiation, the hot afterglow of the Big Bang. Early dark energy proposes inserting a new chapter. Imagine that shortly after inflation ended, this extra repulsive field became the dominant component for a brief cosmic instant. This would have given the universe an extra, powerful kick of expansion during its first few 100,000 years. This extra push would have subtly changed the conditions during two critical events: Big Bang nucleosynthesis and the formation of the cosmic microwave background. Big Bang nucleosynthesis is the process in the first 20 minutes where the first atomic nuclei, like hydrogen and helium, fused. The amounts produced depend exquisitely on how fast the universe was expanding and cooling. An early dark energy episode would have sped things up, slightly altering the primordial helium abundance. The cosmic microwave background, the snapshot from 400,000 years later, would also bear its imprint. The extra expansion would affect how sound waves traveled through the primordial plasma, changing the statistical patterns or peaks we see in that ancient light. If we adjust our models to include this early kick, the predicted expansion rate from the cosmic microwave background can shift upward, potentially aligning with the faster rate measured from supernova and Cepheid stars. It is a cosmic fudge factor that makes the numbers work. The challenge is that this field had to be incredibly fine-tuned. It had to emerge, dominate the universe completely, and then decay away into radiation almost perfectly, leaving the subsequent cosmic evolution untouched until dark energy re-emerged billions of years later. We are looking for the ghost of a force that came and went in a blink, its only evidence frozen into the primordial abundances of elements and the subtle harmonics of the universe's first light. Experiments are now scouring both domains for hints. Precision measurements of the cosmic microwave background from observatories like the Atacama Cosmology Telescope and the Simons Observatory are analyzing those harmonic peaks with microscopic detail, searching for the specific distortion an early dark energy boost would leave. Meanwhile, astronomers are using the world's largest telescopes to measure the primordial helium and deuterium abundances in the most ancient, pristine clouds of gas in the distant universe, seeking a discrepancy from standard predictions. Finding evidence for early dark energy would be a monumental discovery. It would mean that the acceleration of the universe is not a one-time event, but a recurring theme in cosmic history, a force that can awaken in different strengths at different times. It would elegantly resolve the Hubble tension by revealing that our standard model missed a crucial, dynamic episode in the universe's first second. More than that, it would connect the universe's explosive birth to its accelerating fate, suggesting that the same mysterious physics that shaped our beginning is also writing our end. The search for a unified theory of physics has been called the Holy Grail of science, a single set of equations that can describe everything from the dance of subatomic particles to the majestic sweep of galaxies. This is the quest for quantum gravity, a framework to marry Einstein's theory of general relativity, which governs the very large, with quantum mechanics, which governs the very small. And standing right at the crossroads of this epic challenge is dark energy. In fact, the cosmological constant, that simplest form of dark energy, is not just a problem for quantum gravity, it is a natural prediction of it. Quantum field theory tells us that empty space should be alive with energy. Therefore, a true theory of quantum gravity must inherently include a description of the vacuum and its energy. The staggering failure is that when we try to calculate that number, we get an answer 120 orders of magnitude too large. This is not a minor bug, it is a screaming alarm that our understanding of reality is fundamentally broken at the deepest level. So how do the leading candidates for quantum gravity approach this catastrophe? String theory, perhaps the most famous contender, proposes that the fundamental ingredients of the universe are not point-like particles, but tiny, vibrating strings. The different vibrations of these strings correspond to different particles and forces. To make the math work, string theory requires extra spatial dimensions beyond the three we experience, curled up into shapes so small we never notice them. The properties of our universe, including the value of the vacuum energy, are determined by the geometry of these hidden dimensions, and here is where dark energy becomes entwined with a breathtaking, and for some troubling concept, the string theory landscape. The theory suggests there is not one unique solution, but a colossal number of possible stable configurations for these extra dimensions, each corresponding to a universe with different physical laws and constants. This landscape may contain a staggering 10 to the power of 500 different possible vacua, each with its own value for the cosmological constant. In this view, our universe, with its inexplicably tiny, non-zero dark energy, is simply one island in a near-infinite archipelago of possibilities. We do not explain why the number is small. We just note that in such a vast landscape, every possible value will occur somewhere. Our existence selects for one of the rare islands where the numbers allow for galaxies and life. This is the multiverse answer taken to its logical extreme. Loop quantum gravity, a major rival to string theory, takes a different path. It does not invoke extra dimensions. Instead, it proposes that space itself is not smooth and continuous, but woven from tiny, finite loops, a fabric of discrete quantum threads. In this picture, there is a smallest possible unit of space, a quantum of volume. This granularity of spacetime at the Planck scale could potentially prevent the vacuum energy from adding up to infinity, offering a natural cutoff that might solve the calculation problem. The hope is that from this quantum geometry, the small observed value of dark energy could emerge naturally as a property of the woven cosmos itself, rather than as a random draw from a cosmic lottery. Both approaches are profoundly abstract, operating in realms far beyond direct experiment. They represent humanity's most ambitious attempts to heal the rift between the quantum world and the cosmos. Dark energy is the bridge between them, a measurable effect in our accelerating universe that points directly to a gaping hole in our foundational physics. To solve the dark energy mystery may not require a bigger telescope, but a deeper theory, one that can tell us why the hum of empty space is so quiet and what that silence truly means. That search for a deeper theory often begins with a single, stubborn piece of data. Long before we mapped the acceleration of distant galaxies, a mystery was unfolding right here in our own solar system. The Pioneer anomaly refers to a tiny, persistent tug that seemed to be slowing two of humanity's most distant robotic envoys. As Pioneer 10 and Pioneer 11 sailed beyond the orbits of the outer planets on trajectories that would carry them into interstellar space, radio tracking revealed something odd. Both spacecraft were experiencing a minute, unaccounted for deceleration back toward the Sun. It was an incredibly small effect, about 10 billion times weaker than the gravity we feel on Earth's surface, but it was there, and for years it defied explanation. To the scientists analyzing the data, it felt like a whisper from the void, a hint that our understanding of gravity might be incomplete on the scale of the solar system. Could this be a local sign of the same physics driving cosmic acceleration? The most tantalizing idea was that it represented a modification to gravity, a subtle deviation from Einstein's predictions that would become noticeable in the weak gravity environment of the outer solar system. Some theorists proposed that certain models of modified gravity, designed to explain dark energy without invoking a new substance, could naturally produce such an anomalous pull. The Pioneer probes, acting as unwitting test particles, might have been the first to feel it. This turned the anomaly into a potential bridge, connecting the vast cosmic acceleration to a measurable effect in our own celestial backyard. It was a thrilling possibility. However, science has a rigorous process for separating signal from noise. After years of meticulous detective work, a team of researchers dove into the decades-old engineering data, reconstructing the thermal environment of the aging spacecraft. They discovered that the heat generated by the probe's radioactive power sources and onboard electronics was not radiating away perfectly symmetrically. A tiny fraction more heat was being emitted from the back of the spacecraft's dish antennas than from the front. This anisotropic thermal radiation acted like a faint photon rocket, providing just enough gentle, continuous thrust to explain almost all of the observed deceleration. The mystery, it seemed, had a mundane, mechanical answer, yet for some, a whisper of doubt remains. Could there be a tiny residual effect, a sliver of the anomaly that thermal radiation does not fully explain? And if so, could that sliver be the fingerprint of new physics? The legacy of the Pioneer anomaly is profound, regardless of its ultimate cause. It demonstrated the incredible precision of solar system navigation and showed how even the most subtle effects can be hunted down. It forced theorists to sharpen their models because any proposed modification to gravity had to now pass this local test. A theory that predicted an anomalous acceleration 10,000 times larger than what Pioneer saw would be instantly ruled out. In this way, the humble Pioneer probes became critical gatekeepers. They set stringent limits on how much gravity could be modified within our solar system, pushing the possible explanations for dark energy further out onto the truly cosmic stage where galaxies fly apart. The probes taught us that if dark energy is a sign of modified gravity, its effects must be vanishingly small locally, only revealing their full power in the immense voids between galaxies. Their silent journey continues, carrying not just a golden plaque for any distant civilization, but a lesson etched in data. Sometimes the greatest cosmic mysteries are first sensed as the faintest of tremors close to home. The faint whispers from our own solar system fade into a much larger, more unsettling pattern written across the entire sky. Deep within the cosmic microwave background, the most pristine snapshot of the infant universe, astronomers have found something that should not be there. They call it the axis of evil. This ominous nickname refers to a series of strange, large-scale alignments in the ancient light, patterns that seem to pick out a preferred direction in the cosmos and directly challenge one of our most sacred assumptions. For over a century, cosmology has been built on the Copernican principle, the idea that the universe is isotropic, meaning it looks the same in every direction. The CMB is supposed to be the ultimate proof of this, a nearly perfect uniform glow. But when scientists subtract that perfect average, the tiny temperature fluctuations left over, the seeds of future galaxies, reveal a bizarre secret. Certain patterns of hot and cold spots appear to be aligned along a particular axis, a kind of cosmic spine running through the universe. Even stranger, this axis seems to be curiously aligned with the plane of our own solar system and the direction we are moving through space. The odds of this happening by random chance in an isotropic universe are incredibly low, like rolling a die and getting a 6 100 times in a row. So what could this mean? The most conservative explanation is that it is a colossal statistical fluke. Our observable universe is just one bubble within a much larger cosmos, and we simply happen to live in a region where the primordial fluctuations, by pure luck, lined up in a peculiar way. It is an unsatisfying answer, but one that remains possible. A more profound possibility is that it is a sign of pre-Big Bang structure. Perhaps our universe is not the first and only one. If it was born from a prior cosmos or as a bubble in an eternal multiverse, the imprint of that larger environment could have been stamped onto our CMB, breaking perfect isotropy. The axis of evil would then be a fossil, a scar from a time before time, a window into a cosmos that existed before our own. Then there is the most unsettling idea of all for dark energy research. Could this alignment be related to dark energy's influence? If dark energy is not a perfectly smooth, uniform force, but has subtle variations or textures across space, it could have imprinted a directional preference on the expansion history of the universe, leaving a faint trace in the way the CMB light traveled to us. It would mean the force accelerating the cosmos is not featureless, but has a structure we are only beginning to glimpse. The axis of evil is more than a curious anomaly. It is a direct assault on the foundation of modern cosmology. If it is real and not an artifact of how we process the data or a trick of foreground dust in our galaxy, it forces a humbling realization. We may not live in a perfectly smooth, featureless cosmos, but in a place with a preferred direction, a cosmic north that hints at a reality far stranger and more complex than our simplest models allow. The eerie alignments in the ancient light force us to look forward to a future where dark energy's work is complete. This brings us to a pair of intertwined mysteries about the ultimate fate of everything we see and everything we know. The first is the future of cosmic structure. Right now, our universe is a vibrant tapestry of galaxies woven into clusters and superclusters by gravity. But dark energy is the great unraveler. As the acceleration continues, its repulsive force will eventually overcome gravity's pull on the very largest scales. The growth of the cosmic web will halt, no new superclusters will form. Then the isolation begins. As space stretches at an ever-increasing rate, the threads connecting galaxy clusters will snap. Each cluster, like our own local group of galaxies, will become an island universe, adrift in a rapidly expanding void. The most profound change will be in the night sky. Today, we can see light from galaxies billions of light years away. But as the expansion accelerates, there will come a time when light from galaxies outside our own gravitationally bound cluster can no longer reach us. The space between us and them will be stretching faster than light can travel across it. One by one, distant galaxies will redshift into invisibility, their light stretched to wavelengths longer than the universe itself. Their images will freeze, then fade to black. In a future trillions of years from now, any astronomers in the Milky Way will look out and see only the dim, aging stars of our merged galaxy, surrounded by an impenetrable, eternal darkness. The universe will have become a collection of isolated island universes, each unaware of the other's existence, their histories forever sealed off. This leads directly to the second, more philosophical mystery, the fate of information. In our current universe, the light from distant galaxies carries information about the past. We learn about cosmic history by collecting photons that have traveled across space for billions of years. But in the dark energy-dominated future, that information pipeline is severed. When a galaxy crosses the cosmological horizon, its light can no longer reach us. It is not just that the galaxy disappears from view. Every bit of information about its stars, its planets, its potential history is lost to our island universe forever. It passes beyond a point of no return. This creates a cosmic-scale information paradox. In physics, information is generally considered to be conserved. It may change form, but it is not destroyed. Yet in an eternally accelerating universe, the information from entire galaxies seems to vanish permanently beyond an event horizon, much like matter falling into a black hole. Stephen Hawking famously wrestled with whether information is lost in black holes, a problem that shook physics to its core. The accelerating universe presents a similar but vastly larger conundrum. Will all knowledge of cosmic events beyond our local cluster be erased? If so, does the universe ultimately enforce a kind of cosmic amnesia, where the full story of existence becomes unknowable to any observer in any island? Or does the information persist in some form we cannot yet comprehend, encoded in the fabric of space-time itself at the boundary of our horizon? The accelerating expansion does not just threaten to freeze the cosmos, it threatens to erase its own memory, leaving future civilizations with only the faintest ghost of a story, a single chapter from a book whose other pages have been torn away and burned in a fire moving faster than light. The potential erasure of cosmic information pushes against the very limits of what our theories can describe. And this tension reaches a fever pitch in one of the most abstract and consequential debates in modern physics. The conflict centers on a set of ideas known as the swampland conjectures. In the quest for a theory of quantum gravity, physicists envision a vast landscape of possible consistent theories. But the swampland is the treacherous region surrounding that landscape, a theoretical no-man's land filled with ideas that look promising but are ultimately inconsistent, that cannot be connected to a complete theory of quantum gravity. They are dead ends. The conjectures are a set of proposed rules for staying out of the swamp, a checklist for viable theories. And one of the most impactful of these rules deals a direct blow to our simplest explanation for dark energy. A leading swampland conjecture states that any stable dark energy, like a true cosmological constant, must be incredibly weak, or more precisely, that its potential energy must be extremely flat. But the conjecture goes further. It suggests that a perfectly constant, unchanging dark energy with a value as small as the one we observe might actually be impossible. It would place our universe squarely in the swampland. This creates an immediate and dramatic crisis. Our best astronomical observations strongly favor a dark energy that is constant, that fits the cosmological constant model beautifully. Yet one of our best guides to a deeper theory of quantum gravity seems to be telling us that such a thing cannot exist. It is a direct, high-stakes clash between two pillars of modern science: astronomical observation and fundamental theory. Proponents of the swampland ideas argue that this tension is a feature, not a bug. It is a powerful clue. It tells us that dark energy cannot be a simple cosmological constant, but must be something dynamic like quintessence. In this view, the near-constant behavior we see is just a slow roll, a temporary plateau on a changing landscape. The universe's acceleration will not last forever in its current form because the theory says it cannot. This would force a radical reinterpretation of our data and our cosmic destiny. Critics, however, see it differently. They argue that the swampland conjectures, while intellectually compelling, are not yet proven laws of physics. They are informed guesses based on our current, incomplete understanding of string theory. To throw out the remarkably successful cosmological constant model based on a conjecture, they say, is to put the cart before the horse. Perhaps our observations are telling us that the conjectures need to be revised, or that our universe finds a clever loophole. The debate is more than academic. It defines the future of cosmology. If the swampland conjectures hold, then our meticulous measurements of supernova and galaxy clusters are not just refining a number, they are hunting for the first definitive sign of a change, the first wobble that proves dark energy is dynamic. A failure to find such a change, even with next-generation telescopes, would be a massive blow to these theoretical ideas. We are witnessing a profound philosophical standoff. Do we trust the smooth, elegant fit of a constant dark energy to the data, or do we trust the elegant, theoretical principles that claim to guide us to a deeper truth? The swampland is not a physical place, but a conceptual battleground where the fate of our cosmological model, and perhaps of string theory itself, will ultimately be decided. The clash between observation and theory brings us to a line in the sand, a boundary so strange it is named for the supernatural. This is the phantom divide, the point where the equation of state parameter W drops below -1. It is the mathematical threshold that separates a strange but stable cosmos from one destined for absolute demolition. Crossing this line means dark energy is not just constant, but growing stronger, denser as space expands. This is phantom dark energy, and its implications are as terrifying as they are fascinating. In this model, the repulsive force does not dilute as the universe grows. Instead, it intensifies. The more space stretches, the more powerful the phantom field becomes, creating a runaway feedback loop of acceleration. This leads inevitably to the Big Rip, not in some unfathomably distant future, but in a finite, calculable time. Depending on how far below -1 the value lies, the entire universe could be torn apart in a matter of tens of billions of years, a sudden end on the cosmic clock. The phantom divide is more than a prediction, it is a theoretical crisis. In most standard models of physics, a substance with W less than -1 violates what is known as the null energy condition. This is a fundamental rule that, roughly speaking, says energy should not be able to flow faster than light, and that exotic matter with negative energy should not be stable. Phantom energy shatters this condition. It behaves like a substance with negative kinetic energy, a concept that makes physicists deeply uncomfortable because it can lead to unstable quantum fluctuations, causality violations, and universes that are fundamentally unpredictable. It opens the door to theoretical monsters like wormholes and time machines running rampant. So the question is stark: does our universe flirt with this phantom line? Current observational data from supernova, the cosmic microwave background, and galaxy clustering is incredibly precise. It tells us that W is very, very close to -1. The best fits consistently land right around -0.98 or -0.99, with error bars that still comfortably include -1 itself. We have not yet detected a definitive, statistically significant crossing. The data allows for phantom behavior but does not demand it. The universe, for now, seems to be teasing us, hovering just on the safe side of the supernatural brink. But the hunt for a phantom signal is intensifying. Every new galaxy survey is essentially a more sensitive probe of this critical number. If future data, with 10 times the precision, finally pushes W definitively below -1, it would trigger a revolution in fundamental physics. We would have to accept that our universe is filled with a substance that breaks our most cherished energy conditions. It would force us to radically rewrite quantum field theory or general relativity to accommodate this phantom reality. The phantom divide is not just a line on a graph. It is the frontier between a cosmos that ends with a slow freeze and one that dies in a violent scream. Our measurements are the needle on the dial, inching closer to an answer that will either confirm the universe's ultimate stability or reveal that its very foundation is built on phantom energy, waiting to unleash its final catastrophic rip. That phantom line between stability and chaos is a boundary we may never cross, but it forces us to confront the sheer improbability of our own existence. The unnerving fine-tuning of dark energy, that it is just strong enough to accelerate the cosmos but weak enough to allow for galaxies and life, points toward a staggering possibility. Perhaps our universe is not alone. The 17th mystery asks if dark energy is our most compelling evidence for the multiverse. In this view, our cosmos is just one bubble in an infinite, frothing sea of universes, each with its own random set of physical laws and constants. This idea emerges naturally from two of our most ambitious theories. Eternal inflation suggests that the rapid expansion that launched our Big Bang never truly stopped everywhere. Instead, it continues eternally in a background space, spawning new bubble universes like bubbles in a boiling pot, each a separate Big Bang with potentially different properties. Meanwhile, string theory's landscape of possible vacuum states, numbering 10 to the 500 or more, provides a vast catalogue of possible universes. In this cosmic archipelago, every conceivable value for the cosmological constant exists somewhere. Universes where it is positive and large blow apart instantly. Universes where it is negative might collapse in a big crunch. Our universe, with its peculiarly tiny, non-zero value, is simply one of the rare habitable islands where the numbers allow stars to shine and planets to form. From this perspective, dark energy is not a puzzle to be solved with a single equation. It is a cosmic lottery ticket. We do not need to explain why the number is so perfectly tuned. We just happen to live in one of the infinitesimally few universes where the tuning permits observers like us to exist and wonder about it. This is the anthropic principle applied on a multiversal scale. It swaps a physics problem for a statistical reality. Unsurprisingly, this explanation is deeply controversial. For its proponents, it is a powerful, even elegant solution. It naturally explains the fine-tuning not as a miracle, but as a selection bias. We should not be surprised to find ourselves in a universe compatible with our existence, any more than a fish should be surprised to find itself in water. It removes the need for a single, special theory to justify one specific number. For critics, however, it is a philosophical surrender. They argue it makes cosmology untestable and unscientific. If every possible universe exists, then any observation we make, no matter how unlikely, is guaranteed somewhere. the theory predicts everything and therefore predicts nothing. How could we ever falsify the idea of an unseen infinity of universes? The debate cuts to the heart of what science is. Is the multiverse a legitimate scientific inference from the data of fine-tuning and our best theories? Or is it a metaphysical speculation that moves beyond the realm of empirical inquiry? Some scientists hold out hope for indirect evidence, like finding a bruise on the cosmic microwave background from a collision with another bubble universe in the distant past. Others believe the answer lies in a deeper theory that makes our vacuum energy inevitable, rendering the multiverse unnecessary. For now, dark energy sits at the center of this storm. Its inexplicable value is either a profound clue that we live in a staggeringly special universe, demanding a revolutionary explanation, or it is a mundane fact of our address in a reality so vast that every possibility is realized. The mystery of dark energy may not be about what it is, but about where we are. The multiverse offers one answer to fine-tuning, but another clue may be written in our motion through the cosmos. The 18th mystery is the dipole anisotropy, a lopsidedness in the universe's oldest light that reveals we are not standing still. When astronomers map the cosmic microwave background, they expect to see a perfectly uniform glow, the same temperature in every direction. But they do not. One half of the sky is very slightly warmer, the other half very slightly cooler. This pattern, called a dipole, is mostly explained by a simple fact. Our entire solar system is moving at a blistering speed of about 670,000 kilometers per hour relative to the rest frame of the CMB. We are rushing toward the constellation Leo, and like running into a light rain, photons from that direction appear blue-shifted and warmer, while those behind us appear red-shifted and cooler. This is the Doppler effect on a cosmic scale, and it accounts for the vast majority of the signal. But here is where the mystery deepens. When scientists subtract this expected motion from the data, some studies suggest a residual dipole remains, a smaller but significant lopsidedness that should not be there. This could be mere statistical noise, or it could be something far more profound. One tantalizing explanation is a bulk flow, a colossal river of galaxies thousands of times larger than our local group, all moving together in the same direction. Imagine you are in a boat on a wide, calm ocean. You expect the water to be still, but if you and everything around you are being carried by a vast, unseen current, your local measurements would be skewed. A bulk flow would mean that dark matter and the galaxies it holds are not evenly distributed on the largest scales, but are being pulled by the gravitational tug of something unimaginably massive beyond our observable horizon, a supercluster of cosmic proportions. This would directly challenge the cosmological principle that the universe is homogeneous. If such a flow exists, it could imply that dark energy is not perfectly smooth either, that its repulsive push might vary across space, creating textures and gradients that gently steer the motion of entire galactic superclusters. The evidence for these mega flows is hotly contested. Some galaxy redshift surveys have reported motions consistent with a flow extending out to billions of light years. Other, more comprehensive studies find that the motions cancel out, supporting the standard model of a mostly uniform cosmos. The debate hinges on painstaking measurements of galaxy distances and velocities, trying to separate the expansion of the universe from the peculiar motion of galaxies swimming through it. Is the residual dipole just a fluke, or is it the fingerprint of a cosmic current, a hint that our universe has a large-scale structure so immense we can only see its gravitational wake? The answer will tell us if we are passive passengers in a perfectly smooth expansion, or if we are caught in a dark river flowing towards something we cannot yet see. The vast currents that may flow through the cosmos began with the first elements forged in the universe's fiery dawn. Among the ashes of the Big Bang lies a tiny, stubborn discrepancy known as the lithium problem, a mismatch that could whisper secrets about dark energy's ancient past. In the universe's first 3 minutes, a process called Big Bang nucleosynthesis cooked the primordial soup of protons and neutrons into the first atomic nuclei. The predictions for hydrogen and helium match the observed cosmic abundances with stunning precision, a triumph for the Standard Model. But for lithium-7, the third lightest element, the math fails. The universe contains only about 1/3 of the lithium that our theories say it should. For decades, this has been a headache for nuclear astrophysicists, a puzzle confined to the study of the early universe. But what if the lithium problem is not just about nuclear physics? What if it is a clue about the expansion rate of the universe during those critical first minutes? This is where the shadow of dark energy reaches back in time. The amounts of each element produced depend exquisitely on how fast the universe was expanding and cooling. A faster expansion would have shut down the nuclear fusion processes earlier, leaving less time to build elements like lithium-7. Could an episode of early dark energy, that brief, supercharged kick of expansion some theorists propose to solve the Hubble tension, also be the culprit behind the missing lithium? If a dynamic dark energy field flared into existence and sped up the cosmos during nucleosynthesis, it could have quenched lithium production at just the right level to match what we see today. This creates a tantalizing link. One exotic modification to early universe physics might solve two unrelated problems: the tension in today's expansion rate and the ancient deficit of a primordial element. It is a cosmic 2-for-1, where the fingerprint of dark energy's ancestral form is etched not in distant galaxies, but in the very chemistry of the oldest stars in our own galaxy. Astronomers search for this primordial lithium in the atmospheres of ancient metal-poor stars, relics from near the dawn of time. Their surface chemistry is a frozen record of the early universe's composition. The persistent shortfall they see is a silent signal, a message in a bottle from the first 3 minutes, waiting for the right key to decode it. Perhaps the key is not a better nuclear reaction rate, but a revised history of the cosmos itself, one where the force that now accelerates the universe first stirred in its infancy, subtly altering the recipe for creation. That missing lithium is a chemical echo of the universe's first moments, but to trace dark energy's full story, we need a map of everything it has done since. This leads us to the 20th mystery, a powerful geometric test that uses the universe's largest structures as cosmic yardsticks and funhouse mirrors. It is called the Alcock-Paczynski test, and it offers a way to measure dark energy by watching how space itself distorts the shapes of galaxy clusters over cosmic time. The principle is elegant in its simplicity. Imagine you are looking at a distant spherical cluster of galaxies. You can measure its size in two ways, along your line of sight and across the sky. To measure its depth, you use the spread of the galaxy's redshifts. The difference in redshift between the front and back of the cluster tells you how physically deep it is, because that spread is caused by the expansion of the universe across the cluster's own vast width. To measure its width across the sky, you simply use its angular size, how many degrees it spans in your telescope. In a universe with a simple, predictable geometry, these two measurements should agree, giving you a perfect sphere. But dark energy warps this geometry. It changes how distances relate to redshifts over the history of the cosmos. If we assume the wrong cosmological model when we convert redshifts into distances, the sphere will appear distorted. It might look squashed along our line of sight or stretched sideways. The Alcock-Paczynski test is the act of looking for that distortion. By surveying millions of these large-scale structures at different distances, and thus different eras, astronomers can essentially perform a cosmic tomography. They can see how the apparent shape of these standard spheres changes as we look back in time. A clear trend in the distortion becomes a direct measurement of the universe's expansion history, and therefore of dark energy's strength and constancy. This method is beautifully independent of the supernova distance ladder. It does not rely on understanding the intrinsic brightness of dying stars. It relies purely on geometry and the statistical properties of structures we believe were roughly spherical when they formed. It is a cross-check written in the architecture of the cosmos itself. Upcoming surveys are poised to unleash this test with revolutionary precision. The Dark Energy Spectroscopic Instrument, or DESI, is already collecting spectra for tens of millions of galaxies, mapping the three-dimensional universe in unprecedented detail. The Vera-C, Rubin Observatory's legacy survey of space and time, will image billions of galaxies, providing the perfect catalog for applying the Alcock-Paczynski test on a staggering scale. By combining these datasets, scientists will construct a distortion map of the universe across billions of years. If dark energy is a true cosmological constant, the distortion pattern will follow one specific curve. If dark energy is dynamic, the curve will bend differently. The universe's largest spheres, held up against the light of history, will reveal whether the force stretching them apart has always been the same, or if its grip has been tightening or loosening since the dawn of time. While the universe's largest structures act as geometric yardsticks, the oldest light in the cosmos carries a far more subtle imprint of dark energy's work. Photons from the cosmic microwave background have been traveling for over 13 billion years, and their journey tells a story written in the faintest of whispers. As these ancient particles fly toward us, they must pass through the evolving cosmic web of dark matter and galaxies. When a photon falls into a deep gravitational well, like a massive galaxy cluster, it gains energy, appearing slightly hotter. When it climbs back out, it loses that energy, appearing cooler. In a universe where gravity alone controls the expansion, these gains and losses perfectly cancel out over the course of the long journey. The well deepens as the photon enters, but it also deepens as the photon leaves, so the net effect is zero. But dark energy changes the rules. It causes the universe's expansion to accelerate, which weakens the gravitational grip of these large-scale structures over time. A cosmic well begins to decay and flatten as the photon is climbing out of it. This means the photon loses more energy climbing out of a shallowing well than it gained falling into a deeper one. The result is a net loss, a tiny, additional cooling of the CMB photon. This subtle, cumulative effect is called the late-time integrated Sachs-Wolfe effect, and it is a direct, unique signature of dark energy at work. It is not just evidence that the universe is expanding, but proof that the expansion is accelerating, written into the oldest light we can see. Detecting this signal is an exercise in extreme precision. Astronomers cannot see it in a single photon. Instead, they must search for a statistical correlation across the entire sky. They take a map of the cosmic microwave background's temperature variations and overlay it with a map of the large-scale structure of the universe from a galaxy survey. They then look for a specific pattern. Do the slightly cooler spots in the CMB tend to align with the locations of the most massive galaxy clusters and superclusters? That alignment is the telltale sign of the late-time ISW effect, the shadow of decaying gravitational wells cast upon the primordial light. It is like listening for a single, quiet note played by a specific instrument in a grand symphony. The hunt has yielded tantalizing, but not yet definitive, results. Several studies have reported a correlation consistent with the predictions of our standard model with dark energy. The signal is there faintly in the data, but it is not yet strong enough to rule out the possibility of statistical fluke or contamination from other sources, like dust in our own galaxy. This leads to a profound question. What if, with better data, the signal vanishes? A non-detection of the late-time ISW effect would be a monumental crisis. It would suggest that the gravitational potentials of the cosmic web are not decaying as expected. This could mean one of two shocking things. Either dark energy does not exist, and the acceleration we see from supernova has another, even stranger cause, or our understanding of gravity on the largest scales is fundamentally wrong in a way that also mimics acceleration. The integrated Sachs-Wolf effect is more than a technical measurement. It is a direct bridge between the universe's ancient light and its modern structure, a bridge whose stability depends entirely on the silent, repulsive force that now governs our cosmic expansion. Finding its imprint confirms the story we think we know. Not finding it would mean the story is far stranger than we ever imagined. The quiet hum of empty space may not be the universe's final word. There exists a theoretical possibility so absolute that it makes even the Big Rip seem like a gentle end. This is the vacuum decay catastrophe, the idea that our entire cosmos is living on borrowed time, not because of expansion, but because of a flaw in the very nothingness that fills it. According to quantum field theory, the vacuum state we inhabit might not be the true, lowest energy state of reality. It could be a false vacuum, a precarious plateau of energy, like a ball resting in a shallow dent on the side of a mountain. Our universe seems stable only because the ball has not yet found the deep valley far below. Quantum physics, however, allows for a process called tunneling, where particles can spontaneously jump through energy barriers. In this case, it would be a bubble of true vacuum of lower energy that could spontaneously form anywhere at any time. This bubble would then expand at the speed of light in all directions. Its wall would be a boundary of fundamental change. As it passes, the laws of physics as we know them would be rewritten. The constants that govern forces, particles, and chemistry would be permanently altered. Atoms would cease to hold together. Every structure, from galaxies to DNA, would instantly dissolve into a new, alien configuration of matter and energy. There would be no warning and no escape. The entire observable universe would be erased and replaced not with emptiness, but with a different reality whose rules we cannot comprehend. The stability of our vacuum and the likelihood of such a decay depends critically on the precise shape of the universe's energy landscape, a landscape where the value of the dark energy or cosmological constant is a key feature. Some calculations suggest that if dark energy is a true cosmological constant, our vacuum might be stable for an unimaginably long time. But if it is a dynamic field like quintessence, the potential for a catastrophic transition could be higher. It is a chilling reminder that the force accelerating the cosmos could also be the one holding the knife to its throat, its parameters quietly determining whether our universe endures or vanishes in an instant. This ultimate fragility of reality connects to a more subtle but equally profound puzzle about the nature of time itself. Why does time have a direction? We experience it flowing irrevocably from past to future, a river carrying us from memory toward possibility. This arrow of time is embedded in everything from the spreading of milk in coffee to the aging of stars. Yet in the fundamental laws of physics, from Newton to Einstein to quantum mechanics, time is symmetric. The equations work just as well running backward as forward. So where does the arrow come from? The answer, most physicists agree, is entropy, the tendency of systems to move from order to disorder. But entropy needs a stage on which to play, and that stage is the expanding universe. The relentless growth of space, driven in our era by dark energy, provides the ever-increasing volume that allows entropy to keep rising, creating the thermodynamic gradient that gives time its direction. In a static, unchanging universe, entropy would eventually maximize and the arrow of time would effectively vanish. Processes would become reversible, cause and effect would blur. The cosmological constant, by ensuring eternal expansion, guarantees that the universe never reaches this final equilibrium. It is the engine of time's arrow. This leads to the deep quantum mystery. In attempts to formulate a quantum theory of the entire cosmos, time often becomes a problematic variable, something that emerges from a more fundamental, timeless reality. How does the smooth, flowing time of our experience arise from the frozen equations of quantum gravity? The accelerating expansion and the dark energy behind it may be the key link between the timeless quantum birth of the universe and the directed, entropic time we live within. We are carried forward on a river whose current is dark energy, and its flow may be the very reason we remember a past and anticipate a future at all. These vast, silent chambers of near-nothingness are not just empty space. They are the universe's dominant architecture, making up over 80% of its volume. While galaxies cluster into brilliant filaments and walls, the voids between them are incomprehensibly huge, some stretching hundreds of millions of light years across, with only a handful of isolated galaxies drifting inside. This near-perfect emptiness makes them pristine laboratories, places where the subtle tug of dark energy and the possible flaws in gravity can be seen with unparalleled clarity. Within a dense galaxy cluster, gravity's pull is fierce and complex, a storm of interactions. But inside a void, the environment is simple, quiet, and profoundly underdense. Here, the repulsive push of dark energy faces almost no competition from the gravitational pull of matter. If dark energy is a constant force inherent to space, its effect should be most pronounced in these regions, causing the void to expand faster than the universe as a whole. The walls of the void should be stretching apart more rapidly. Astronomers are now measuring this by painstakingly mapping the shapes and galaxy populations of thousands of voids. They look for a telltale sign, a squashing or stretching in the void's apparent shape when viewed from our perspective, using a geometric test similar to the one applied to galaxy clusters. The results are beginning to paint a picture. Some studies suggest the largest voids are indeed expanding faster than the standard model predicts. They appear slightly more elongated along our line of sight, as if dark energy is giving them an extra powerful kick. This could be a direct confirmation of dark energy's uniform push, but there is a twist, a whisper of something stranger. If gravity itself is modified, if Einstein's equations break down in these incredibly weak field environments, the voids would behave differently. In some alternative theories, like certain versions of modified Newtonian dynamics extended to cosmology, gravity becomes slightly stronger in extremely low-density regions. This would act to slow the void's expansion, pulling its sparse galaxies together more than expected, making the void appear less empty over time. So the crucial question becomes, are the voids emptier or fuller than they should be? Projects like the Dark Energy Survey and the upcoming Euclid Space Telescope are conducting cosmic void censuses. They are not just counting voids, they are weighing them. By studying how the few galaxies inside a void move, and by measuring how light from distant sources is warped as it passes through these empty regions, a technique called weak lensing, they can infer the total gravitational pull and thus the total mass of the void itself. The preliminary answers are provocative. Some of the largest voids seem to contain even less matter than our best models predict. They are emptier than empty. This could be the signature of dark energy's overwhelming dominance, or it could be the first hint that gravity weakens where matter vanishes, allowing the void to inflate like a balloon with less resistance. Every new void mapped is another data point in this grand experiment. We are learning that to understand the force that fills the cosmos, we must first understand the profound, accelerating nothingness at its heart. The profound emptiness of cosmic voids forces us to look back to the very beginning, to the moment when all of space was smaller than an atom. That first instant holds a puzzle so deep it required a revolution to solve it, and its solution may be whispering to us across all of time. This is the horizon problem. When we look at the cosmic microwave background, the afterglow of the Big Bang, we see a sky of nearly uniform temperature. Yet, according to the standard Big Bang model, regions on opposite sides of the sky were never in contact. They were separated by distances greater than light could have traveled in the age of the universe at that time. How could they have reached the same temperature if they could never exchange heat or information? It would be like walking into a perfectly coordinated dance where the dancers have never met or practiced together. The elegant solution proposed in the 1980s is cosmic inflation. This theory suggests that in the first tiny fraction of a second, the universe underwent a period of exponential, faster-than-light expansion, driven by a repulsive energy field called the inflaton. This violent stretching smoothed out all wrinkles, set the same temperature everywhere, and planted the quantum seeds that would later grow into galaxies. Then the inflaton field decayed, its energy transforming into the hot soup of particles of the Big Bang, and inflation ended. But here lies the 25th and perhaps most profound mystery. Could the story of that first field have a second chapter? Could dark energy be the distant, faded echo of the inflaton? This speculative idea is known as quintessential inflation. It proposes that a single, dynamic energy field is the protagonist of our entire cosmic saga. In this model, the field first powered the ultra-rapid inflation of the universe's birth. Then it went dormant or rolled into a shallow valley, hiding for billions of years while matter and radiation ruled. Now, in the present epoch, as the universe has expanded and diluted, that same field has reawakened, rolling into a new, nearly flat part of its landscape where its repulsive push is gentle but persistent. It is the same actor playing two roles, the explosive force of creation and the quiet force of eventual dissolution. The implications are staggering. It would mean the universe's first instant and its ultimate fate are woven together by one continuous thread. The same physics that set the stage for galaxies to form is now writing the final act of their isolation. The timeline of the cosmos would not be a series of disconnected eras, but a single, coherent narrative driven by the evolution of this one fundamental entity. This connection is more than poetic. It offers a potential resolution to the fine-tuning problem. Perhaps the value of dark energy is not random, but is a natural consequence of how the inflaton field settled down after its initial frenzy. Its incredibly small strength today might be mathematically linked to the enormous energy it unleashed at the beginning. The field's journey from a steep hill to a gentle plain could naturally produce the universe we see. Of course, this remains highly speculative. We have no direct evidence for the inflaton field itself, let alone that it survives to the present day. The energy scales involved are unimaginably different. Inflation operated at energies a trillion times higher than those associated with dark energy. Bridging that gap requires theoretical gymnastics that many physicists find difficult to accept. Yet the allure is undeniable. It promises a unified story, a theory of everything that connects the quantum spark of existence to the vast, accelerating emptiness of the future. It suggests that by understanding the dark energy that now pushes the galaxies apart, we might finally be decoding the final message of the force that created everything from nothing. The horizon of our understanding stretches back to the first moment, and the force that solved that ancient mystery may be the very same one now drawing a veil over the cosmos. The silent story of dark energy is about to be told with a clarity we have never known. Across the globe and in the vacuum of space, a new generation of cosmic observatories is rising, each designed to dissect the accelerating universe with surgical precision. Their mission is not just to measure dark energy, but to trace its history, to watch its influence grow across the eons, and finally answer whether it is a constant whisper or a changing roar. This is the decade we map the shadow. In the mountains of Chile, the Vera Sea, Rubin Observatory is preparing to open its eye to the sky. Its mission is the Legacy Survey of Space and Time, a 10-year, all-sky movie that will capture the entire southern hemisphere sky every few nights. It will not just take pictures, it will detect change. It will find and measure billions of galaxies and track millions of supernovae, watching them flare and fade. Its primary power lies in weak gravitational lensing, As light from distant galaxies travels to us, it is subtly bent by the gravitational pull of all the dark matter and structure in its path. By measuring the tiny, coherent distortions in the shapes of billions of galaxies, Rubin will create the most detailed mass map of the universe ever made, revealing how cosmic structure has clumped and grown under the competing pulls of gravity and dark energy's push. It is like taking an X-ray of the cosmic web across time. Joining this effort from a vantage point 1,000,000 miles from Earth is the Nancy Grace Roman Space Telescope. With a field of view 100 times larger than the Hubble Space Telescopes, Roman will perform its own vast surveys with exquisitely sharp infrared vision. It will peer through the dust of our galaxy to measure the shapes and distances of hundreds of millions of galaxies, performing its own ultra-precise weak lensing survey. But Roman adds a crucial new tool. It will discover thousands of the most distant Type 1 supernova, the same standard candles that first revealed acceleration. By finding these stellar explosions at the very edge of the observable universe, Roman will measure the expansion rate at epochs far earlier than we can currently probe, directly testing if dark energy's strength has changed over cosmic history. Meanwhile, the European Space Agency's Euclid mission is already on its way to the same gravitational sweet spot in space. Euclid's specialty is a combination of optical and near-infrared imaging and spectroscopy. It will chart the three-dimensional positions of over 1 billion galaxies, creating a colossal map of the large-scale structure across 10 billion years of cosmic time. With this map, Euclid will apply the Alcock-Paksinski test with unprecedented rigor, looking for the geometric distortion in vast cosmic voids and clusters. It will also measure galaxy clustering and weak lensing, providing an independent space-based cross-check to the ground-based surveys. The goal is a three-dimensional tomographic scan of dark energy's influence, layer by layer, through the history of the cosmos. On the ground, a different kind of eye is preparing to open. The Square Kilometre Array, or SKA, will not see light at all. It is a radio telescope composed of thousands of antennas spread across South Africa and Australia. Its power is in detecting the faint radio emission from neutral hydrogen gas, the most abundant element in the universe. By mapping the location of this hydrogen in 3 dimensions for billions of galaxies, the SKA will trace the cosmic web in a way completely independent of optical telescopes. It will measure the Barrian acoustic oscillations, those frozen sound waves from the early universe, with phenomenal precision across a vast volume of space and time. This will give us another, completely independent ruler to measure the expansion history, free from any potential systematic errors that might affect optical surveys. Together, these titanic projects are not competitors, but collaborators in a single, unified quest. They will overlap in time and sky coverage, allowing scientists to cross-correlate their data, to check and recheck every potential bias or error. They will provide a multi-messenger, multi-wavelength autopsy of the accelerating universe. Within the next 10 to 15 years, the combined data from Rubin, Roman, Euclid, and the SKA will deliver a measurement of dark energy's equation of state parameter with a precision of 1% or better. We will know definitively if it has deviated from the simple cosmological constant. We will see if it varies with time. We will watch the growth of structure slow under its influence. We are building the instruments that will finally read the signature on the force shaping our destiny, written across the sky in galaxies, in ancient light, and in the silent spaces between everything. From the first instant of creation to the final fate of all things, a single, silent force weaves the story together. This journey through the 25 mysteries of the cosmic dark energy era reveals a cosmos far stranger and more dynamic than we ever imagined. We have traced its fingerprints from the missing lithium in ancient stars to the phantom divide that could tear reality apart, from the eerie alignments in the first light to the vast, accelerating voids that now define our universe. This era, the longest chapter in existence, is not a passive backdrop. It is the active, dominant force shaping our destiny, having already dictated the past and now writing the final, lonely pages of the future. The most humbling truth is that nearly 70% of everything is made of something we cannot see, touch, or even define. We have a name for it, but its essence remains the universe's greatest secret. Yet, this is not an ending, but a beginning. We stand at the threshold of a new age of discovery. The Vera C. Rubin Observatory, the Roman and Euclid space telescopes, and the square-kilometer array are not just instruments. They are time machines and cartographers for the invisible, poised to deliver answers within our lifetime. They will measure the strength of dark energy across the eons, hunt for its changes, and finally tell us if our universe ends in a frozen silence or a catastrophic rip. The mystery that has defined modern cosmology is on the verge of being solved. So stay curious, watch the skies, follow the headlines from these incredible missions, and remember that you are living in the moment when humanity stared into the accelerating dark and decided to map it. Which of these 25 mysteries keeps you wondering? Share your thoughts below and subscribe for more deep dives into the enigmas that shape our incredible reality. The story of the cosmos is still being written, and the next chapter is for all of us to discover.